In this talk, we will talk about in the second part of this talk, we will talk about certain determinantal inequalities that appear quite naturally over the entire TNN Grassmannian. But in the first part, I thought I will talk about certain basic properties about totally non-negative matrices regarding parameterization and how to test for total positive. I hope that's okay. That's going to be okay. So let's begin. So we call a matrix totally positive if all of its minors are positive. And similarly, we call a matrix totally non-negative if all of its minors are non-negative. So now since I plan to discuss about conditions using which we can test for total positivity, since we have Anna Kushnikova and Olga Katkova as one of the participants, I thought I will begin with a sufficient condition that they provide in terms of submatrices of size 2 by 2 for any matrix. So suppose A is any entry-wise positive matrix square, and suppose C is a constant which is equal to 4 times cos square pi over n plus 1. Then if entries in any 2 by 2 submatrix of A satisfy this kind of condition here, then the matrix A is miraculously totally positive. Moreover, the value C here is optimal in the sense that if we reduce the value of C such that these conditions are satisfied, then there would exist some submatrix of A which will have negative or non-positive minor. So since one of the co-authors is here with us, if you want, you can ask why this result is miraculously true. Okay, so let's continue with further. Suppose M and R, I'm going to use some standard notation. So I will use box Mn to denote the set of all integers M through N, box N to denote the set of all integers 1 through N, and I will use A subscript S of T to denote the submatrix in which the rows are indexed by S and columns are indexed by T. I will use A little jk to denote the submatrix in which the jth row and kth column is absent, and k plus or minus S to denote the corresponding translation of the set S. So the first question that I want to address is how to construct these matrices in a rather natural way. So for that, we will basically have to look at directed acyclic planar network which have non-negative weights. Suppose gamma is such a directed acyclic planar network with non-negative weights, which has source vertices u and sink vertices v, where u and v are labeled by integers 1 through n. Now for a given directed acyclic planar network with non-negative weights, we define a weight matrix A gamma, in which the ijth entry corresponds to the sum is equal to the sum over all paths P from vertex I in U to vertex J in V, where WP is the product of weights of edges in the path P. Okay. Now, so this matrix is clearly entry-wise non-negative because all the edge weights are non-negative. However, because of the planarity and because the network is acyclic and planar, it's not very difficult to see that there is a very nice formula to compute the minors of these matrices via a similar formula, which basically says that that the minor of matrix A gamma corresponding to rows I and columns in J is equal to the sum over all families of disjoint paths P from vertices labeled by I to vertices labeled by vertices in J, where WP is again the product of edges in the family of paths P. Now, in particular, because we have this formula and because the edge weights are non-negative, the matrix A is going to be totally non-negative. That's what we have. So for example, let me do an example and show you how this formula works. So suppose we have this planar network on 3 source sink vertices. So edge weights are, so all the horizontal edges are directed from left to right. These edges go down like this and these go up. So this is A, so edge weight is A, B, C, D, E, F. This is D1, this is D3. Then the 1th entry of the matrix. So we write down 3 by 3 matrix with entries Aij.
Sorry, your 1, 2, 3 label up to down or down to up?
Up, down to up. So yeah, so we need to identify all the paths from 1 to 1. So there is only one path here. The weight of that path is just D1. Similarly, we compute A12. A12 is going to be, so there is only one path to go from 1 to 2, which is via this way. So the weight of that path is D1 times F. And so on. So for example, if we compute, let's say A22. So for A22, we want to start at 2 and end at 2. And there are two ways to do that. So one is just straight across, the weight of that path is going to be D2. And the other is we step down one step, go horizontally, and then go up. So B times D1 times F. So let me compute some of the views here. For example, A13 is going to be D1FE. So because there's only one way to do that, D1FE. And A21 is going to be similarly B times 1. A31 is going to be A, B, E1. And so let's compute bigger minors. So for example, what is going to be A12, A12? So we want to look at all the paths that originate at 1, 2 and end at 1, 2. But we want the families of paths to be disjoint, vertex disjoint. So in this case, there is only one way. There is only one family of path, and the weight of that family of path is just D1 times D2. And similarly, we can compute A.
You're saying this is equal to your formulas for A11 times A22 minus A12 times A21.
That's right. And this is equal to, so let's say, so this matrix is it'd be CD, whatever.
You use ABC.
What are ABC?
You just use.
Even A11,
the way-
A12.
So yeah, so this is, so let me write it. What do I mean by this? This is determinant of A. I was using a short. So A12 is D1 times. And if A3 by 3 is this is just AB minus BC. This is going to be equal to that. Question. Is this okay?
Notations are not good, but
You mean it's A11, A12?
A is
It might be nice not to
you have
use
A,
A,
B.
B, C, and D.
as
The A11,
yes,
A12. A11, A12, just say that. You have the formulas.
Oh,
Oh, it's
well, yeah.
Similarly, this is B times D1 times C times D2. And finally, the determinant of the matrix. Okay, so these little A2, 3, 1, 2 refers to the determinant corresponding to these rows and these columns. And determinant is going to be just D1 times D2 times D3 because there is only one way to move from 1, 2, 3 there to 1, 2, 3 here. We need to compute 4, 6, 8. No. Let me just check. I have a. So I want to compute one more. I have A1, 2. 3. And compute the other if I need. So yeah, so that's the gist of this result. Now, so what we just saw is that if we have a directed acyclic planar network with non-negative weights, then we have a totally non-negative matrix. The converse of this result is also true in the following sense. So for that, we need some notation. So we use the elementary matrices EUV, in which the UVth entry is 1 and the rest of the entries are all zeros. And using that, we define the elementary bidiagonal matrices. So what are these matrices? These are essentially identity matrix in which exactly possibly one of the immediate off diagonal entry is going to be non-zero or positive, non-negative. So using bidiagonal factors and elementary bidiagonal factors like these, there is this theorem due to Lohner and Whitney, which basically says that any n by n non-singular totally non-negative matrix A can be factorized into products of these elementary bidiagonal factors and a diagonal matrix with positive diagonal entries. And moreover, they also show that set of all totally non-negative matrices is basically the limits of all totally positive matrices. Okay. Now, so using this result, how do we construct the corresponding planar network for any given totally invertible totally non-negative matrix? For that, what we do is that we construct planar networks corresponding to each of the factors here, which is not very difficult. For example, if we want to construct the planar network corresponding to this elementary factor identity plus WE54, then it's not very difficult to check. This graph over this planar network here represents the matrix above it. And similarly, for a diagonal matrix with diagonal entries D1, D2, D3, and so on, the given the planar network drawn below it represents that matrix. So once we have the planar networks corresponding to each of these factors, using Cauchy-Binet formula, we can simply concatenate these elementary elementary planar networks, construct the planar network corresponding to matrix A. Although we'll have to be careful because we'll have to concatenate these planar networks in the same order of these factors as they are for the matrix A. So for example, if we construct the corresponding planar network for 5x5 totally non-negative matrices, they would look something like this. And more generally, for n by n totally non-negative matrices, the planar network would look something like this. Now at this point, now I want to discuss about how to test for total positivity and what were the ramifications.
Sorry, could I ask a dumb question? These pictures look very symmetric. Was that in the statement?
So the EI minus is the transpose of.
But the A you're starting out with is symmetric or?
No,
No,
it's not.
it doesn't have to be. Okay, very good. Yeah, thank you.
Parameters could be different.
The follow-up. So the first product on the lower triangular side is from 1 to n minus 1. The outer product on the upper triangular is from n minus 1 to 1.
That's right.
But then the inner products are in the they are also in different orders.
Yeah.
Okay. So then it's really symmetric.
Okay, so I hope it's not going to be very difficult. So by the way, how many parameters do we have here? Exactly n square. How many entries do we have in the matrix? N square. Now the question is, so first point is that if each of these parameters here are positive, then the matrix that we have is totally positive. So, and using, so Projesh mentioned one result. It basically said that if all the initial minors of any totally positive matrix are positive, then the given matrix is totally positive. Using planar networks, so what is happening there is that because the initial minors are positivity of the initial minors imply the positivity of these parameters here.
And contiguous.
So these initial minors I talked about contiguous. He's talking about initial. Oh, you didn't mention initial. So yeah, there is a result which says that if all the initial minors of any matrix are positive, then the matrix is totally positive. So what initial minors really do, now that we know of planar networks, is that initial minors make each of these parameters positive. And because of that, the matrix becomes totally positive. So it's not something very special about initial minors. It is because they make each of these parameters positive, we have total positivity. So for example, if we look at these minors that I computed here earlier, this is an initial minor. So if this is positive, D1 has to be positive. This is another initial minor. If this is positive, then F has to be positive because D1 is positive from the previous condition. This is another initial minor. Now, if this is positive, then E has to be positive. And so on. We continue. D1 is positive, so B has to be positive. Like this, here we'll have A positive. Here we'll have D2 positive. Here we'll have D3 positive, and so on. So what we really need is a collection of n square minors, which force each of the parameters here be positive to have total positivity. For example, there is another collection of 3 square minors. If my computation is correct, these minors are A31, A32, A12, A13, A2312, A3, 2, A1323, A123, and A123. Now, if my computation is correct, if these n square minors are 3 square minors are positive, then each of the parameters are going to be positive. But some of the minors that we have here are not initial. So
No. Initial?
initial.
What do you mean by initial?
So this is a matrix. This is your, let's say, a matrix. Initial minor would be something like this. It would either touch this side of the matrix or this side of the matrix, and it will not be discontinuous in choosing the rows or columns in any way.
Okay,
Yeah.
this is initial.
These are initial minors. So yeah, so there is another collection of n square minors which will force these parameters to be positive. And this is where this was the observation of Fogman and Zelewski, among many other things, is that was this, and that they were also able to establish a very nice connection between these n square minors, these types of n square minors, with the positivity of which implies total positivity. And that connection was established using Fogman and Zelewski. Found very nice connection. These sets of n square minors via something called double wiring diagrams. So when you make a double wiring diagram, you will have phase labels. They call that those phase labels correspond to the minors, these minors, and they call those chamber minors. And we need some relation between chamber minor. And to move from one set of n square minors to another set of n square minors, they used some things, things called local moves. And these local moves basically change the collection of minors using certain determinantal identities. And not only that, they were basically, if you think about it, if you take any generic matrix and you take one of these n square collection of minors, then that generic matrix is uniquely determined by these n square minors via, because each entry is going to be a Laurent polynomial with non-negative coefficients in terms of these minors. So I'm not going to go into the details, but that's what really inspired, or more, I mean, that's what really inspired them, Fomin and Selevinsky, to discover cluster. This, among other connections, led them to discover cluster. So yeah, my plan was to discuss reach somewhere close to cluster algebras. So yeah, so this is where I basically stop. And I conclude this section by showing some combinatorial totally non-negative and totally positive matrices. So if we just consider Pascal's triangle and construct these two matrices, so the first one is simply writing a matrix in which each of the rows correspond to each of the rows in the Pascal's triangle appended with zeros. And the first one is going to be totally non-negative. And the second matrix, this is constructed by writing each of the rows in the Pascal's triangle as each of the anti-diagonals in the matrix. Then the matrix that we get is totally positive. Similar results, similarly constructed matrices for Stirling numbers, Narayan numbers are also totally non-negative and totally positive. And there is, people have researched much more about these kind of matrices. However, the same result remains open for Eulerian numbers. So if you're not familiar with Eulerian numbers, please Google. So yeah. So this is where we conclude the first part. So for the next part, I'm going to talk about oscillating system of inequalities via temporally leaf eminence, and eventually we reach towards Plücker inequalities. Okay. So for this, consider, for example, consider 4x4 totally non-negative matrix. So consider a 4x4 totally non-negative matrix. Write down its determinantal expansion along its first row. So what we have here, so yeah, so first row is important because we don't know what happens in the second row yet. So we do that expansion. Then because matrix A is totally non-negative, the last term in this expansion, which is minus A14 determinant A14, is not, it's possibly, is a non-positive term, is a non-positive term. So if we remove that term from this expansion, we get an inequality which holds over all 4x4 totally non-negative matrices. This was not very difficult to see. However, the pattern continues in the sense that if we remove the next term, which is A13 determinant A13, we again get an inequality. However, now the sign of the inequality is reversed. And it's not very clear why this is happening until we write down the proofs. The pattern continues, and that is, if we remove the next term, we again get an inequality, and the sign of the inequality has been reversed again. And the last inequality is also known as the Fisher inequality.
Was Fisher's inequality for TNN or PSD or symmetric? What matrices?
Sure. Okay, so this basically, yeah, this inequality, these set of inequalities were discovered by Garnwacker Grime and are written in their book on oscillating matrices. So the general result is that you take any n by n totally non-negative matrix, you write down its Laplace expansion, partial Laplace expansion along the first row. Along the first row is important. Then, depending on the length of that partial Laplace expansion, you get an inequality which is either greater than the determinant or less than the determinant of the matrix. So so in my recent work with my former postdoc mentor Sean Fallett, we took this result and we thought to generalize it. We generalized it for the expansion along any first D rows of any totally non-negative matrix. And we were able to show that similar set of oscillating inequalities exist. We also explored several other identities to obtain these kind of oscillating inequalities, like Carlin's identity and others similar to Laplace identity. And we were able to obtain these kind of oscillating determinantal inequalities. Now, in this talk, we will see that that we will basically sort of have tried to so that how that there is a very fundamental phenomena behind the existence of these oscillating determinantal inequalities. And for that, we will have to work over the totally non-negative part of the Grassmannian. And we will have to look at the long Plücker relation for that. So let's review that Grassmannian M, M plus N is a manifold of M dimensional vector subspace of Rm plus N. So each of the vector, this manifold can be identified with the collection of tall full rank M by N, M plus N by M matrices modulo column operations. I mean, you can look at it as a wide matrix as well. I look at it as a column matrix. So for me, the Grassmannian M plus N is just the collection of full rank tall matrices modulo column operations. And the maximal minors of maximal size of these tall matrices are called Plücker coordinates. And these are related via very nice relations called Plücker relations. So I'm going to state these Plücker relations in a bit more generality. I mean, in the sense that we need them. So suppose I and J are ordered M element subsets of bracket M plus N. And suppose K and R are integers in the set of integers 1 through M. And we construct these sets IKR and JKR. So how do we construct them? We look at IR in I and JK in J, and we swap their positions in the coordinates. So and then with these sets constructed, we can write down these relations, and delta ij times delta I times delta j is equal to sum over k is equal to 1 through m of delta ikr times delta jkr.
For every R.
This is true for every R.
Depend on R.
And yeah, so we look at these relations for any R, any fixed R. Now, to look at
The I and the J are ordered tuples, but they need not be in increasing order or decreasing order.
ordered as
The
in
indices
they
need-
have, yeah, so they need not be, yeah. They are different from
Substitute anyway the ordering.
we need the order matters. Yeah, so the way we want to look at these the Plücker relations is that first of all, we need to find a way to order how delta IKR and delta JKR appear in the Plücker relation, because we want to delete or add these terms one by one to obtain inequalities. And once we order them nice enough, we want to find a place where we can put delta I and delta J on the right hand side with at some nice midpoint among the terms on the right hand side. So that's what we are looking to do. And I will show you, like using combinatorics, the way we will present this order and this location, you won't be able to do anything better than that. Like whatever inequalities one can write using these terms in the Plücker relation, I will be able to show very trivially that those inequality, whatever one has written, can be obtained from what we have very trivially. That comes from the combinatorics. That's a bit implicit. Anyway, so let me show you. So let's recall what is the TNN Grassmannian, what is the relation between them and the TNN matrices. So TNN Grassmannian is basically the collection of those tall matrices in which all the Plücker coordinates are non-negative. Okay. So now to see the connection between TNN matrices and the TNN Grassmannian, suppose if we basically look at this map, which maps every totally non-negative matrix A to this matrix A bar, which is essentially A appended with matrix W0, where W0 is that anti-diagonal matrix in which the first entry at the bottom is -1 to the power m plus 1. Next entry is -1 to the power m plus 2, and so on. So with this embedding,
So it is the signed longest word permutation matrix.
that's right. So with this map, one can see that there is a one-to-one correspondence between minors of A and the maximal minors of A bar. So because of this reason, A bar is in the TNN Grassmannian. Okay, and that the one-to-one correspondence is given by this map over here. So one doesn't have to read that because I'm going to discuss nice way to identify these the connection between minors and Plücker coordinates. For example, if we have that, I mean, if we are familiar with this notion, then I can skip this part. Okay, then I'll do a few examples. So for example, so if A is that 3x3 matrix and we want to embed it inside the TNN Grassmannian, so let's see how we can see the first entry in the matrix. So A11 is essentially determinant A with rows index 1 and column index 1. So what we basically do, we draw this circle. It's easier this way. So 1, 2, 3. So these indices correspond to rows, and here we have columns. So first, so the row index here is 1. Okay. So we check that. The column index here is 1 as well. So this is 1, 2, 3. We check that. Now what we are doing is that we move from this side to here. So 1, 2, 3. This is 4. This is 5, and this is 6. So the column index here is 1. We complement it. What do we get is 2, 3. Complemented, and then we look at the bracketed index, that is 4, 5. So this is Plücker coordinate 1, 4, 5. That is exactly we have there. So if you compute this minor, you will get exactly the first entry in the matrix A. Similarly, to look at 1, 2, 2, 3. So 1, 2, 2, 3 correspond to, so 1, 2 remains 1, 2. For 2, 3, we look at 2, 3. Complemented, we get 1. 1 identifies with 6. So we get 6 here. So this minor corresponds to this Plücker coordinate. So that's how it is. That's how the correspondence works. And yeah, if you want further details on TNN Grassmannian and how it is divided into positroid cells, please have a look at this paper, or I'll also be very happy to chat about this paper. So yeah, so with this correspondence, it's not very difficult to see that in order to study determinantal inequalities over totally non-negative matrices which are in products of two minors, it is equivalent to study determinantal inequalities which are in products of Plücker coordinates for these representative matrices over again for totally non-negative matrices A, and is further equivalent to study determinantal inequalities that are in products of Plücker coordinates over the TNN Grassmannian. And this comes from the geometry, comes from the projective geometry of the Grassmannian.
So the difference between the last line and the second last line is the last line is equivalence classes modulo some GLM action. When this holds in the second last line, it actually holds.
Yes, and because we have like these are quadratic inequalities, so the same factor comes out from both of these coordinates and it squares, it becomes square. So that's why we can ignore that square term. It may not work for cubics. So yeah, so So why do we have to look at this? Because we know the classification for the first type of inequality. And the first type of inequalities are exactly equal to the second type of inequalities. So we will show the second type of inequalities and we'll conclude that the third type of inequalities hold. So that's the plan. Okay, so now let me discuss the result, main result. So suppose M and N are integers and we have two M element subsets of ordered M element subsets of set bracket M plus N. Now, as I said in the beginning, that we need to order the elements of I minus I and J carefully to obtain these inequalities. So what we have is that, so once we pick the elements of I and J, we locate the elements of I and J on the circle with points 1, 2 through M plus N. And we call I and J weakly separated if I minus J and J minus I can be separated by a chord in that circle. So what do I mean by that? Let me show one example with one example. So suppose M is N and is 6. And suppose I is 2, 3, 4, 9, 11, 1. And J is 5, 8, 7, 12, 6, 10. So we draw the circle. 1, 2, 3, 4, 6, 7, 8. So we have 2 as I, 3, 4, 11. So now we can see that we cannot separate the elements of I and J by drawing a chord anywhere. However, on the other hand, if I prime is something like 11, 12, 3, 4, 1, 2, and J prime is 5, 6, 7, 8, 9, 10, then we can separate these elements because so 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. So 5, 6, 7, 8, 9, 10. These are all the elements of J, and these are all in I. So this set is weakly separated. Now, once we define weak separability, we define the order of the elements in I minus J and J minus I. So what do I mean by that is that we want to cut this circle at some point in between dot and this non-dot part. So if we cut here, this becomes my I1, I2, I3, I4, I5, I6. And this is J1, J2, J3, J4, J5, J6. And similarly here, this can be my I1, I2, I3, I4, I5, I6. And similarly, this is J1 and all the way to J6. So this is how I'm using. I mean, this is the kind of ordering I need, in which the terms delta IKR and delta JKR appear in equality. So once we set all of this up, I have again IKR and JKR, which is similar to the way it is in the Plücker relation. So what I'm really doing here is just finding some nice order in which these terms will appear in the Plücker relation and give us inequality. So once we do all this, here is the result. So once I have fixed the order in which elements of I and J minus I appear, so we take a partial sum in the long Plücker relation up to some length. So this is that midpoint that I was talking about, where the term delta I and delta I times delta J appear in that expression. So we basically have these types of inequalities. Now, the interesting part here is that I will talk about the inequality. I'll present some examples, but the fact is that these inequalities hold only when I and j are weakly separated, and the weak separability is a phenomena which is very closely related to the cluster algebra of the Grassmannian, in the sense that, so to define the cluster algebra of the Grassmannian, one needs to start with some initial cluster and then mutate, and until the end, until you generate all the coordinate ring of the Grassmannian. Now, one cannot start with any arbitrary collection of Plücker coordinates to reach there. And it turns out that there is a classification which says that the initial cluster has to have the Plücker coordinates in the initial cluster has to be a collection of weakly separated Plücker coordinates. So it seems that the notion of weak separability, which is very closely related with the cluster algebra of the Grassmannian, also related with the existence of these Plücker inequalities. But we don't know these connections yet, but that's there. And maybe we can do something in the future. So, okay, so now let's briefly talk about the idea behind the proof. So for this, we will need a temporally Lieb imminence. So what are these? These are basically given a complex number psi, and we define temporally Lieb algebra to be the complex algebra generated by elements T1, T2, Tn minus 1, subject to these three relations. Now, this algebra can also be seen as a quotient of Hecke algebra, which is a complex algebra with parameter q and so on. And so these are the relations. I'm not going to read that because it's sort of well known. But the fact is, now what I want to present here is that the elements. So what are the standard basis elements in Tn psi? So these are basically the monoid, and good monoid Bn generated by these elements T1, T2, Tn minus 1, subject to those relations. So how does one see these basis elements? So you basically look at all 3 to 1 avoiding permutations in Sn, and in that 3 to in those, and look at the corresponding words. In that word, you replace each Si with Ti, and that's how you will be able to see all the basis elements in Tn psi. So for example, if let's say I want to look at, and another way to visualize the basis elements is via wiring diagrams. Suppose I want to look at T1, T2, T3, T1, then T1 is represents this wiring diagram. T2 is this, T3 is this, and T1 is this. Now what we do is that we replace each of these crosses with these kind of structures. Okay. Once we do this, these become now if we look carefully, this is one edge, so this is equal to this. If we keep track of this one here, this one is here, because so sorry, this one here, we can see that there is a, so this is just this one, and then here we have this guy and this line. Okay, so each basis element give rise to some non-crossing partition. Okay, so this represents a non-crossing partition on 4 elements. So similarly, I mean, there is, so you may want to look at this one your own and ask me if you have some question here, because this one is interesting. Okay. So yeah, and therefore the dimension of the Tn psi is the nth Catalan number. given by that formula. So yeah, this is just some basic notion about temporally leaf algebra. So how do we define temporally leaf imminent? So first we specialize psi is equal to 2, in which case Tn2 becomes isomorphic to a quotient of the symmetric group algebra itself via the homomorphism where Si is mapped to Ti minus 1. Using that homomorphism, we define these functions f tau, which goes from Sn to R, where f tau omega, f tau w is the coefficient of tau in sigma omega for every basis element tau in Bn. So what I'm doing here is that I want to define f tau at omega. And there is an image of sigma omega. So omega, write omega in using the generators. So sigma omega is just the product of Ti minus 1s. You multiply them out, and then you look for tau in that multiplication. And then the coefficient there will give us f tau of. Using, now that these functions are defined over Sn, we write this, we write the formula for the temporal leaf imminence. Now, first of all, these functions are different from the character imminent, because in the sense that these are not class functions, but yet they are still quite fundamental because of the results that follow. So once we have defined temporal leaf imminence, it's not very difficult to see that determinant corresponds to the imminent, temporally leaf imminent for the unit element. Okay, so it generalizes the determinant. And moreover, all of this construction is due to Rhodes and Scandera, in which they further show that temporally leaf imminents are a basis of the space, which is the vector space in which each element is just the products of complementary minors. Okay.
Unit element means it takes value 1 at every permutation.
The unit element T1 to the power 0. Moreover, they showed that all temporal leaf imminents are totally non-negative. That means these imminents are going to give non-negative values whenever evaluated totally non-negative matrices. And moreover, they show that if we want to classify these types of inequalities, which we want to, then all we have to do is to identify the corresponding linear combination of temporal leaf imminents. And if that linear combination happens to be non-negative, then we have an inequality. Otherwise, we don't. So this is the result that we are going to use. And they also gave a very nice combinatorial way to keep track of these temporal leaf imminents. And how do we keep track of those? Let me discuss that with an example. So suppose we want to identify all the temporal leaf imminents corresponding to minor 2, 3, 4, 5 times 1, 6, 7, 8. Then what do? Is that we draw this circle, mark the vertices in 2, 3, 4, 5, and 1, 6, 7, 8 in 2 different colors. And then we draw edges, bicolored edges, so that the edges do not intersect and they stay inside the convex hull of that circle. In this case, we get only one way to draw these matchings. Okay, not edges, matchings. Because 2, 3, 4, 5 and 1, 6, 7, 8, they form contiguous intervals. There is only one way to draw these matchings. So this product of minors is equal to imminent tau 1, where tau 1 identifies with this particular non-crossing partition, as I described here. It's something like this, of different kind. Similarly, if we want to identify the imminents corresponding to 1, 3, 4, 5 times 2, 6, 7, 8, then we again draw these circles with 2 different colors like these, and we draw the matchings. In this case, there are 2 possible matchings, and one matching matches with the Kaufman diagram above. So that one needs to keep. So what I'm trying to say here is that the shape of the edges is what really matters. We don't have to worry about the color of the vertices once we have drawn the Kaufman diagrams. So now finally, if we want to identify whether the difference of these 2 products form an inequality over the corresponding Grassmannian, TNN Grassmannian, then we just have to look at the difference between the corresponding imminents on the right-hand side. And here it turns out that we just get imminent tau 2 which is a non-negative, which is non-negative, which is totally non-negative. And therefore, this basically means that we have a determinantal inequality over the TNN Grassmannian 4-8. So yeah, so we basically use this idea to prove the inequalities that we want to prove. So we consider a very simple case where I is 1, 2, 3, 4 and j is 5, 6, 7, 8. If these are I and j, then delta I times delta j is just one, corresponds to just one Kaufman diagram, because again, we have two intervals. There is only one possible matching. And next, next term in the Plücker relation is delta I1R times delta J1R, in which case, so the red colored vertex here is essentially black. I've colored it differently because I want to keep track of the vertex that is moving. Because if you remember, we are exchanging IR and JK. So IR switches place with JK one at a time. So we have imminent tau 0 plus imminent tau 1 for the second, for this product of minors here, where we get two non-crossing partitions corresponding to two basis element in the temporal leap algebra. So for the first inequality, we'll have to take the difference of the second minus, we'll have to take the difference second minus the first one. And that is basically equal to the difference of the corresponding imminents, sums of imminents. And that is non-negative because, and that is therefore not totally non-negative because the resultant is just imminent tau 1. Okay, so for the third inequality, we again look at delta I2R, delta J2R, and we again draw the Kaufman diagram. And we again do the substitution as we did earlier. And we again get an inequality because the resultant is minus imminent tau 2 this time. And similarly, we do the next step. And the last step is just involves the long Plücker relation itself, which we don't have to verify. Now, to show some pattern, let's look at what we just saw. So what we really saw is that I and J were like 1, 2, 3, 4, 5, 6, 7, 8, and so on. And in identifying the inequalities, we made these substitutions. And we evaluated the algebra after these substitutions. So the reason I've colored these imminents differently is to show that certain telescoping phenomena is happening here. Okay, so for example, delta Ij has imminent tau 0, delta I1 J1 has imminent tau 0 plus imminent tau 1. Now, imminent tau 1 appears in the next product as well, along with something new. Now, that something new appears in the next one, along with something else, which is new. So so the inequalities that we have essentially correspond to an imminent, each of them. And for that reason, these are totally non-negative. That's why we get the inequalities. So to show this phenomena once again, let me use a slightly more complicated example. So suppose K and L are like these. I'm not going to draw the pictures now because I'm sure we can do that by us. I mean, it's not very difficult to do. Now here we get slightly larger number of imminents because of the example that I've chosen, and because of some reason that I have not addressed here. So what's happening is that if you keep track of, so if we disregard imminent tau 0, for instance, then one can easily see that there is a telescoping phenomena that's going in there. Because for that reason, the first inequality is just the blue colored imminents. The second inequality is just the red colored imminents. The third inequality is just the green colored imminents. The last one is just the magenta colored imminents. So these inequalities, we precisely know what these are. These are sums of either one imminent or two imminent. I mean, in the general case, we also get just one or two. We don't get any more for the case of weakly separated I and J. So it is this telescoping phenomena that was happening in Gahnmacher-Krein's inequality as well, which we can now completely capture by basically defining the long Plücker relation for weakly separated Plücker coordinates over the entire TNN Grassmannian. So to now conclude, let me go back to Klein-Marker-Krines inequality with a slightly new perspective, which easily refines to the expansion, determinant expansion for other rules. So we know that determinant A is this expansion. So the new way to look at this expansion is that you move the determinant part with the diagonal term A11 determinant A11 term. And then you start deleting terms from one of the ends. And you will get these set of inequalities. So what is a new inequality here? You expand the determinant along the second row. And you move the determinant term with the A22 determinant A22 term. And then you delete one term at a time from the right hand side or left hand side, whichever. And you'll get these inequalities. This was not known and was not trivial as well. I mean, as far as I'm concerned. Stop here.
So, thank you very much for your talk. We are on time, so time for questions.
I had a question to the first part. To compute, given a matrix, to compute this graph, is this a Neville elimination technique?
Yeah. So it
So
is some kind of elimination. So what you do, instead of eliminating from the top, eliminate from the bottom. You make, that's the idea.
Yeah.
So then the numbers as a 4 cosine squared pi over n+1 in the first, they also appear somewhere else, no? In the subfactor business of John's.
Yes.
And also the Temperley algebra appears because the idempotents satisfy this in basic construction satisfy these relations. Is there any? So there's like a bipartite graph that you can associate and a dual bipartite graph. So there's like these dual pictures, and is there also a dual way like of getting a dual to the first result, this
The
theorem?
first result? You mean
I don't know, but this
this first result?
cosine squared pi over n+1 is
Yeah, I think that question is for
It's exactly the same.
and it also it comes from graph. I mean, you associate a graph to subfactors, so there's like modules that you tensor together, and then depending on how they behave, then you get two graphs, and then you end up with the eigenvalues of this graph, and then you get exactly these numbers.
no, I see. Is that so?
Will also occur in continued fractions.
Where's
No,
the time?
Okay, so but like the Temperley algebra also appears naturally in this context. So
Not sure. I'll have to see.
okay. Very interesting. And also there's a lot of combinatorics going on. So afterwards, because it was so complicated, Jones did develop it's called planar algebra. So he associated to this graph a way of what he tangles and how to do things like, I mean, it looks very similar to what you were doing there. So like,
See.
and then they could prove all kinds of theorems about polynomial algebra or factors just using this kind of combinatorics. So you don't have to do any analysis anymore. It's just combinatoric in the end.
Well, the more basic questions. You have these totally non-negative Grassmannians. So what are the subspaces corresponding to these coordinates? Is there geometric significance for the sub-manifold?
So I mean, for example, some stratification result is there. For example, if you fix certain collection of coordinates, I'm not sure if I'm going to be able to answer that question, but yeah. So for example, you fix a certain number of Plücker coordinates, and you look at the set in which those Plücker coordinates are non-zero or strictly positive. Then there is a way to stratify. There is a way to write the whole Grassmannian. Well, not the TNN Grassmannian. At least the TNN part of it into a disjoint union of these positroid cells.
Well, I wonder, the TNN part of the Grassmannian, what's the geometric significance of that? basic question.
I have to see.
Okay, so that's not obvious.
I'm not sure. Yeah, I don't know. I mean, yeah.
There are more recent results proving that some part of that is homeomorphic to a ball and things like that, but it
Mhm.
wasn't studied initially from the. Is it a submanifold? Is it a distinguished? I'm not sure if it was studied in that.
Oh, okay. I can tell you one result. I mean, if that's what. So, yeah.
Well,
So totally non-negative matrices.
it's a short answer.
Yeah, it's a.
Otherwise,
Yeah.
I'll
So
for coffee.
yeah. So we saw the bidiagonal factorization. Okay. So yeah. So what we have is that there is a diffeomorphism now from our n square to our matrices using that map. So you have you basically take those n square parameters. You have those bidiagonal factors which I wrote. These. So this is a particular, like the result is much more general for this diffeomorphism. So you have these n square parameters, you take them and you multiply it out. This map gives you a diffeomorphism, I mean, if you will. But there is a general way to state this result, which involves any two arbitrary longest word in Sn. And then they're shuffling. You shuffle them in any way you want. So that means you basically have these in any order you want. Then you write the same value, same A for that product. And then you get a diffeomorphism from Rn square to n by n dp matrices.
Okay, I'll continue afterwards. More questions?
No, it's a very stupid question. About this theorem. If we have a TNN matrix, yes, it can be written in such a way, and we can find a planar network and so on. But if matrix is not TNN, no, but so I don't understand this basic minors, because you see that some minors are non-negative, then these weights are non-negative, but if matrix was not TNN, at the beginning there is no network, yes.
No, there is network. So network is for any matrix.
Such array, or I didn't,
Like if you allow negative weights, then you have network for any matrix.
in such decomposition.
Yeah, in exactly such decomposition. In any
I know
decomposition,
about this TNN and
I think
about arbitrary matrix. Yes, it also can be written. Yes.
exactly using that elimination from.
There is a certain more general framework for what you are doing with immanence, so-called Schur functions. I will
Okay.
tell you in
Okay, thank you.
generalization.
So I think this is a good place to move the discussion to the coffee. Thank you once more. What does that
I
correspond?
remember the term aptitude, but I didn't know what it means.
So you want to look at the Grassmann 2-3.
Yeah. Well, that's a sphere. Two sphere. And every two-dimensional subspace in R3 corresponds to tangent plane to the point. So that's a parametrization.
Oh, thank you, thank you. I will,
Very different, but still.
So the
What-
constant, and this constant affix also in.
So the TNN.
Yeah, let me think about this.
Because this is the several layers of abstraction. And I no idea how to visualize.
No, no,
that.
yeah, yeah.
Yes,
Yeah, we
I will think about.
Yeah, I'll get back to you tomorrow, yeah.
Yeah,
Tomorrow or maybe today itself, yeah.
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 okay, thank you.